Thank you. So, yeah, as she said, I'm going to be talking about delay modeling and DAG connectivity to optimize airflow performance. But before that, I would like to talk a little bit about myself, just to introduce myself. Uh, I'm a data scientist at Akvelon, which is a contracting company that creates tech solutions for others and hires people from all over the world. That's the commercial that I was asked to say. Currently, I'm a contractor at Reddit. And before that, I was doing my PhD in cognitive science, studying social networks and propagation of negative attitudes, which is something that you're going to see throughout the talk. I really like networks and graphs. But specifically, the problem that I want to introduce today, or want to try to address today, is how very small upstream delays lead to downstream complications at maybe the executive level or at the user level, and lead to messages that I think we've all seen before. To do that, I would like to talk a little bit about ordering socks or ordering something on any platform. That starts with order placement, fulfillment, transportation, warehousing, distribution, and the customer. I think delays can happen at any of these points. Maybe the app is not working correctly, the user can't find something directly in the app. Maybe there's bad weather and transportation gets delayed. Maybe the ID number is not correct and the warehousing things the item gets lost in the warehouse. And all of these things lead to the end customer receiving his package late. The same thing can happen, or similar things can happen when it comes to data. Maybe finding data is really hard. Maybe we don't have a correct catalog of data. The data cadence is not adequate to the questions that are being asked. Maybe DAG reliability and socket allocation are generating delays in some use cases, and all of these ends up with the request or by the end users being delayed, which is something, it's the main issue that we're trying to address here. And you might be thinking that maybe a data catalog, maybe that graph already is giving you some ideas about a solution. Maybe you're already thinking about data catalog. Maybe you're already thinking of things that could be improved in that flow. But I think it's important to consider how to know where to improve specifically. And in order to do that, I think we already have some tools that are very useful for us and they're very simple, like the standard airflow data, like logical dates, operators, start and end dates of normal tasks. And some other data that we can collect, like the products that are being served, query metadata, if we have the types of query and the times of the queries that are being scheduled by the users, dashboard schedules for any end product schedule that we have, and slot availability. After getting or collecting this data, we can also look at the type of DAG that we have. We might have a small DAG, in which case maybe there's no issue there. We might have multiple small DAGs, and I mean hundreds or even thousands of really, really small DAGs that are just a wait operator, a transform of some type, and then an end operator, and or one big DAG, or a combination of both. Maybe you have multiple big DAGs in your organization. And in all of these cases, I think it's very important to capture and get the lineage, see the dependencies of how those DAGs are interacting with one another. You can do this with the lineage backend command or by open lineage are good tools to do this. And this will get you the dependencies that you need for within the DAGs and between those DAGs. Once we have all of this information, we can map it. And here I'm showing a graph of an example data, some example DAG that is created with multiple DAGs. Just looking at it, you can see that in this case, there are multiple teams that have different DAGs for themselves. Some teams are responsible for multiple DAGs. Some of them are more isolated. Some of them have a very linear structure, and some of them are more convoluted. All right, we have our graph, we have our data, we have everything there. What do we do with that data? And I propose, or I give you two tools to analyze them. The first one is queues, which queues are a sequence of people, vehicle, or tasks waiting their turn to proceed. And queuing theory, or the things that we're going to talk about, determines the performance of those waiting lines. Now, it's important to note that wait cannot be eliminated, but it can be reduced to acceptable levels. And those acceptable levels are the ones that you're going to have to define so that you know how and where to optimize your data. Speaking about the queue, just to give you an example again, we have a source, and in our case, it can be an S3 bucket, or it can be the app, or basically any sort of source. In this case, it's just shelves. We have the scheduler, which is going to give us the input, inter-arrival time, which is going to be the time between different tasks, how different tasks are scheduled. The service time is actually the time that the tasks take, and the service channels are going to be the processing tasks, and then we get an output. This is a normal queue or normal line. But in Airflow, the queues are backwards. They start with the run this last, that's the end of the queue. And then we have our service channels, which are the run after loop, also run this. And we have our sources, which is run me 0, run me 1, run me 2. So it's the same thing, it's just backwards. And you have different service channels, which are going to be the processing things in the middle of that DAG. Something that we use when talking about queues is Kendall's notation, and this is super useful when you're considering what things to optimize for. It's not a formula. It makes no sense as a formula, but it gives you variables that you can look at in your own organization to know where to optimize. So you have the inter-arrival distribution, which is how your tasks are scheduled. How is that distributed? How is that distributed in time? It generally looks like a Poisson distribution, where most things are scheduled at the beginning, or most time is spent at the beginning, and it sharply reduces as time goes on. Then we have the service distribution, which would be the runtime of the tasks. How long do they take? Again, this is a Poisson distribution. We have the service channels, which would be the worker tasks, or in DAG terms, it's generally the T for the ETL, the transformations. We have service discipline. In normal queues, this is if you've been on a line and then another line frees up or has less people in it, you can move to that one. That is low discipline. We can have high discipline and you have to wait for yours. We have other sources of other types of discipline or other types of tasks, which you can implement with dynamic scheduling. The max number of tasks is just the tasks in the DAG, and the calling source would be the number of sources that you have. Someone else mentioned that they have again a dynamic source where maybe in your DAG is waiting for a bunch of files in a bucket, and sometimes it's 100 files and sometimes it's 1,000,000 files. So that variability can also be controlled here, and these variables that you're looking here are going to help you determine what variables to modify to help your DAG or your efficiency in your structure. In this case, just as a simple example, you can optimize the queue by simply adding more service channels. So dividing the input and passing it through more service channels could efficientize the DAG just by, again, looking just at the variables, which in more data-related terms, this could mean splitting up the table, splitting up pre-processing, and getting different tasks to do different things. Another way of looking at this, or another way of analyzing it, which is my preferred way, is networks. Networks, as I mentioned before, allow you to check for betweenness of centrality, which are, in this case, are the big nodes. Big nodes, the bigger the node, the more central the node is to the network. And when you map this, you can actually see that some nodes are very central. In this case, they're fact tables, or they're tables that they're just tables. So they're everything depends on those. They're getting columns from there. They're getting data from there. And what happens is that they become central points of failure. Whereas if one of those things becomes delayed for any reason, or fails because of a schema change or any other reason, then the whole network gets delayed because they're so central to the network. You can also see average path length, which is the average number of nodes that a task has to go through. Maybe in your network, the average path length is 2, and there's just a wait and then a processing, and that's it. And that might look efficient, but maybe if you split it up, maybe if you have a larger path length, you could make it so that there is more data in between that you could take advantage of. You can get the max and the min path length just to see where data is going through more tasks or just going straight up. And you can also analyze column usage by query or by team. For example, let's say you have a very big table with of 100 or 200 columns or 1,000 columns, but most people are only using 1 or 2 of them, especially in those central tables. Then you can split that up, you can get that data out, and you can maybe add more tasks, which would look a little more messy in this DAG network, but it would efficientize your network overall. Another thing that this allows you is to see isolated tasks and tables, which is something that you want to consider, and it will depend on your organization. Maybe you want a very dense network where everything depends on each other, and that might be very good because it allows you to not waste anything. No one is running any task twice, because once a task is run, once something is processed, other tasks are feeding into it, or feeding from it, and you don't waste resources. Maybe on the other hand, you want more isolated tasks. You want nothing to depend on each other because things tend to fail a lot. And if it's super dense and it's super connected, then one failure might result in the whole network going down. So this is specific to each organization, but it's something to consider and something that will pop up once you do these graphing. Another thing that is not mentioned there that can pop up with this is directionality and cycles within the graph. So DAGs are supposed to be acyclical, it's in the name. But sometimes if you're doing multiple DAGs and they're connected and you don't see them in the graph view because you have multiple of them and different teams are working on different things, sometimes cycles can appear. And just mapping it out can show you that there might be a cycle, which in theory can't work, but sometimes does, and I've seen it happen. So this view will actually help you understand that. Another thing that we can do is identify bottlenecks and sources of delay. All of these networks, all of these connections that I showed you before can be weighed by the runtime of the tasks. So you can determine which paths are taking longer by the weight of the task. Yeah, so as I mentioned before, these are all mostly in Poisson distributions, which are heavy right skewed. But sometimes you're gonna see, like in Team 6, distributions or tasks that are taking way, way longer than everything else on the task. And just mapping it out can help you see where the delays are happening, what are the tasks that are taking longer, and know exactly where to optimize. Another thing that you can see is overall delays, which is the difference between schedule time and start time. And they might be divided into many different ways, including just by team. And in this case, again, you can see Team 6 has almost no delays. They have almost no tasks as well. They're a very small team. They have very little amount of tasks. And Team 2 is a huge team with a lot of tasks, but also a lot of delays that go up to 23 hours and 20 minutes. This tells you where to talk to and also what tasks to optimize. Something very important is to, when looking at optimizations, once you've found them, once you found where the issues are, where the delays are, is that improvements made after the bottleneck are useless because you're just, it's always remaining starved. It's waiting for more work because the bottleneck is before it. Then any improvements made before the bottleneck are just resulting in more work piling up. So the only way to actually optimize is actually determining exactly where the problem is and resolving it via, optimizing the query or getting to the root cause of the problem. Now, just in general, things to remember, I think, are identifying what type of DAG you have, multiple DAGs, if you have one big DAG, if you have a lot of people working on multiple teams with different instances of Airflow. Establish protocols to capture and update lineage, that's super important, and I think focusing some DES resources on the ETLs might actually benefit us all. Just looking at this data and taking the time to analyze the data might actually result in more efficiency as opposed to just running it as is. You can use queues to find more service channels. You can use networks to find overloaded tasks. Use data to find bottlenecks. And again, optimize at the bottleneck, not before or after. And that's it.
Awesome. Thanks for that great talk. Anybody have questions?
What framework or visualization library did you use for the DAG visualization?
For that one, I used, I used Gephi. So it's super graphical. It has a good.
I have a question. So how did you export all this data? Like, I guess like you're doing it continuously from Airflow.
They're the ones that are exporting it. But yeah, they get it straight from Airflow and from the records that they have from the dashboards and the historical queries that we have for the users.
You mentioned that making improvements from before the bottleneck would result in more work piling up at the bottleneck. So does that mean that if you make improvements at potentially the wrong place, you're actually increasing the problem?
You would see the problem change. It would just pile up before the bottleneck. So let's say you have something extracting from the sources, and then you have your transform task. That is the problem, that it's not transforming correctly, it's not optimized. It's the issue. You're gonna optimize everything before. All the sources are gonna be ready, and then they're gonna have to wait 3 hours for the transform to be ready. So you're not gonna see a change. It's just they're all gonna be waiting, and that's how it's gonna look like.
All right, thanks, Ahuitz.
Thank you.